Hi everyone, I'm Joelle, and today I'm presenting our work called Know Your Attention Maps, Class-Specific Token Masking for Weakly Supervised Semantic Segmentation. It's a work done together with Damien Bort, and we're from the University of St. Gallen in Switzerland. Now, the main topic of this work is weakly supervised semantic segmentation. What I mean by that is taking input image and training a classification network only on image level labels, then generating some pseudo-segmentation mask, then using those pseudo-segmentation masks as supervision for a segmentation network to get a better segmentation object at the end. Now the part we're interested in is this pseudo-mask generation. There are different methods that already do this. The most famous ones or the most used ones are CAM based or some other derivatives, so GradCAM, ReCAM, etc. The problem with those methods is that they usually only highlight the most discriminative part of an image. Here, as you can see, it's only the head of the cat that is highlighted. So if we were to threshold this to use it as a pseudo-segmentation mask, we will end up with something that looks like that is pretty poor and not very well defined. Now there's an alternative approach, which is to use self-attention of a transformer, since it's inherently very interpretable, because the goal of the attention is really to capture spatial dependencies across the entire image. So if we were to threshold, we would get something like that. The problem here is that even though the shapes are better than with the previous methods, there's still the problem of class assignment. So we will never be able to say that, okay, this is the dog and this is the cat, right? So this is where our idea comes from. Our goal here is to enforce class-specific attention within a vision transformer. So here, the challenges are twofold. First, we need interpretable attention maps with sharp object outlines. And second, we need to be able to assign class labels to those maps. So our idea here is first, instead of using one TLS token, we use multiple of those, one for each class in the dataset. We randomly mask those tokens during training to enforce a reliable assignment between TLS token and a class label. Then we append a registered token to the sequence to store global information. And during training, we prune attention heads that are redundant or noisy to have a better pseudo-mask quality. The first part of the method is to really train the vision transformer in a sparse way. What I mean is really to prune or to set to zero some attention heads that are judged as redundant or noisy. So we modify here the multi-head attention by incorporating those learnable gating units to turn off the noisy heads. So instead of concatenating all the heads, we concatenate the gating of the head. So we go really from a multi-head attention that is dense to a sparse one. Second is to randomly mask the CLS tokens during training as well to enforce an assignment between CLS token and the class label. So in each iteration, we randomly mask 50% of the CLS tokens that are not present in the label. And by masking, I mean just setting them to zero to prevent them from influencing the final prediction. And finally, what we are interested in is this upper block. We extract the self-attention of those. We reshape them into image-like dimension. We keep the maps corresponding to the labels predicted by the VIT. We threshold them and we get into one pseudo-mask. And now some results. So here we first evaluate the pseudo-mask. So the second step here is we're still before the segmentation network. We evaluate quantitatively by comparing with other state-of-the-art methods, and we are the best or the second best depending on the sets. On the Pascal VOC, we also have a visual comparison where the shapes are actually quite close to the ground truth, even though it's only the pseudo-mask. We also evaluate the last part of the approach, so the segmentation part. We also compare numerically and visually, and you can see that we are very close to the ground truth here visually, even though some small objects are missing, but the bigger shapes are all pretty accurate. And we evaluate also across different other data sets, remote sensing, medical imaging, general scene understanding. And now to quickly summarize everything, so our goal was to really propose an end-to-end weakly supervised segmentation method that effectively leverages the self-attention mechanism of vision transformer. First we use attention head pruning, and we add a register token to get really sharp, clean attention. And we use CLS tokens masking to get class-specific attention. And we validate our method across a variety of data sets with different number of classes, complexity, and standard benchmarks as well. And this actually demonstrates the robustness and generalization of the method. So if you have any questions, please feel free to email me. Thank you.